In this session, let us see auto transformer. Okay, basically auto transformer is very easy because in our exam, ideal transformer only they will ask. One thing, and second thing is somehow this auto transformer is complicated by saying comparison between auto transformer and single phase transformer, two winding transformer, or comparison between auto transformer and potential divider. These are all not at all required. Okay, first of all, actually within this completion of the board only we are going to complete auto transformer. Okay, and after that we will solve all world gate questions and all extra questions also, and then only to solve one question volume of copper saving will be there. So only for that question there is a probability of coming the question. We are going to discuss that. Okay, now coming to the point, this is auto transformer, and in this let me think of this as A, and just a minute, let me think of this as B, because most of the textbooks has given here A, B, C, let me think of D. Okay, basically one thing many people feel what is the difference between our rheostat. In our machines lab rheostat will be there. What is the difference between rheostat and auto transformer? Okay, so rheostat also kind of wire will be there, in auto transformer also wire will be there. Okay, then what is the difference? For example, in our rheostat of machines lab, resistance is going to be high. Okay, and if I think of this is the machines lab rheostat, inside the machines lab rheostat air core will be there. So relative permeability is unity. So when the relative permeability is unity, automatically inductance will be very less. Actually in our machines lab rheostat also inductance effects will be there, resistance effects will be there, capacitance effects also will be there. But our normal power frequencies, what is power frequency all over the world? 40 Hz to 60 Hz. Okay, so if you think of power frequencies are very less. Under that condition, what is the reactance value? Capacitive reactance 1 by 2 pi FC, frequency is less, so reactance is going to be very high. If reactance is very high, what about the charging currents? Charging currents for the capacitor is going to be very less, so we will neglect it for power frequencies, so capacitance effects will not be there. And let us compare our normal machines lab rheostat and auto transformer. In our machines lab rheostat, resistance of the wire, resistivity of the wire is going to be very high, such that resistance effect will be more, and inside we are not going to have any highest relative permeability material like iron, so it's going to be air core, so relative permeability is less, so inductance effects are going to be less. So the moment inductance effects are less, we are going to model that with resistance only. Now if you come back to here, okay, in auto transformer, what is the winding resistance? We are going to keep the winding with copper. Okay, so winding resistance is going to be less, but inside you are going to have iron. Okay, actually this iron rod has to be closed. Okay, so the moment you have iron here means, for example, if I think of machines lab rheostat, and inside if I insert iron and if I close the iron rod, automatically inductance effects will be more. Under that condition means my machines lab rheostat resistivity is high, so machines lab rheostat resistance is high. If you keep, for example, inside iron and if you close the iron path, means my inductance effects also will be high. Under that condition, both inductance and reactance effects has to be modeled for machines lab rheostat. Okay, now if you take the same machines lab rheostat, insert the iron into it, around it, insert the iron, so relative permeability is more, so inductance effects will be more, and we are going to have that nichrome wire. So let us reduce that wire resistivity to copper. Okay, so machines lab rheostat, insert iron inside, close the iron and reduce the resistivity of the wire to least possible by using copper wire. That is nothing but auto transformer. Okay, so let us see here. In this case, okay, we are going to connect infinite source. Okay, now can you think of at least changing the voltage or frequency of infinite source? No. So voltage and frequency of this is going to be constant. Okay, in this sense RMS value is going to be constant. Now V1 cannot be changed, means that, for example, because of V1 some current will flow. Okay, some current will flow, because of that current some flux will be produced. some flux will be produced. Now the moment this is going to be AC voltage, AC currents will flow, AC flux, alternating flux will be produced, alternating flux, 0 positive mag, 0 negative mag, 0 positive mag, so alternating flux will be produced. Because of that, voltage should be induced or not? Yes. So that voltage is going to be E1. Now, between V1 and E1, what are the elements connected? There are no elements connected. So V1 magnitude equal to E1 magnitude. Okay. For example, if V1 is 100 volts, E1 should be 100 volts. Means of course scaling factor will be there. Apart from scaling factor, for example, 100 flux lines are produced. Okay. Now, for example, if I connect a load here, so if I close the switch, some current will flow or not? Yes, I2 current will flow. So because of this I2, okay, definitely some flux will come. That flux will try to change the net flux pattern or not? Yes. Okay, so because of secondary current of I2, definitely whenever current is there, automatically flux should be produced. Some flux is produced. Now, what primary will do means whatever be the situation for primary, it is very simple. 100 volts, 100 flux lines. If something is trying to disturb my 100 flux lines, primary will take extra compensating current such that that extra flux lines will be killed and same flux line will be maintained. That's what we discussed in our single phase transformer also. So for example, if some flux is trying to disturb my flux, it will take some extra compensating current such that this flux will be killed, this flux will be killed, this flux will be killed. Okay, so at no load and load, what is the flux here? At no load condition, 100 volt, 100 flux lines, black. At loaded condition, secondary flux is coming, but the secondary flux is exactly compensated by primary compensating flux, such that at loaded conditions also operating flux will be same. Now, in order to prove that, means it is going to have transformer action, because basically we have to prove that it is also a transformer, then only we can further proceed in the analysis. For example, as a transformer, in order to say that transformer action is taking place. Okay, so when transformer action is taking place, I can say I have no load condition of single phase transformer, 2-winding transformer, and also loaded condition. For example, at no load, what was the condition we analyzed? EMF per turn in primary equal to EMF per turn in secondary. Okay, now at loaded condition, what was the equation we got? At loaded condition, operating flux should be maintained constant, or armature reaction should not be there. Okay, so in 2-winding transformer, at no load condition, what was the flux? For example, pi naught, 100 volt, 100 flux lines. Now, because of load current, how much is the flux? Again, 100 volt, 100 flux lines. So, operating flux should remain constant. Remain constant. Now, both the things are, for example, if both the things can be applicable to this, then I can say transformer action is taking place. Okay, for example, see here, in in deriving this, in single phase transformer, we took some time, but here we need not take any time, because, for example, this is 2-winding transformer. In 2-winding transformer, induced voltage here is E1, induced voltage here is E2, and number of turns are N1, number of turns are N2. E1 by N1 equal to E2 by N2. Okay, but here actually in 2-winding transformer we struggled a bit, but here we need not. For example, see here, if I have 100 volts here, okay, if I have 100 turns here, 100 volts, 100 turns, EMF per turn is how much? 1 volt. So 1 volt, 1 volt, 1 volt, 1 volt. So at each and every turn, EMF per turn will be there. Okay, so see here, for example, if I have 100 volts and 100 turns, what is EMF per turn? 1 volt. Okay, so EMF per turn is 1 volt, 1 volt, 1 volt, 1 volt. For example, if I touch here, Is this primary or secondary? One side it is primary, other side same winding is there on secondary also. So it is also going to be 1 volt only or not? Yes. Okay. So for example, see here, this is going to be AB is connected with only primary, and BC is combined between primary and secondary. For example, part of BC winding, is it related to primary or secondary? Both. Combined winding. Okay. So the moment it is winding is combined, EMF pattern on primary side same, no EMF pattern on secondary side also will be same. Okay. So I can say that first condition is fulfilled. EMF pattern in primary equal to EMF pattern in secondary. Now secondary condition already we know. For example, if some load is connected, because of that load, for example, if load flux is coming, no, because of that, is there any net variation of flux? No, means some load current is coming, load flux is coming, that is exactly compensated by primary compensating current. So there is no armature reaction, we can say, or kind of like, operating flux of to auto transformer is going to be constant like two winding transformer. So we can say that transformer action is taking place. Okay, transformer action is taking place. So because of these two transformer action we are going to consider. Now next thing is, see in this AB is separate winding which is separately associated with primary, and BC is combined winding between primary and secondary. So AB is separate winding and BC is going to be combined winding. Now we have to add one more thing. What is that isolated winding? For example, AD. Okay, this AD, is it related to primary or secondary? Nowhere. It is completely isolated, nowhere connected either with primary or secondary. For example, if you think of here, okay, this particular EMF pattern. Okay, so this particular turn also is being influenced by change in flux or not. 0 positive max, 0 negative max, 0 positive max, 0 negative max. So here also EMF pattern will be induced or not. Yes. Okay, so basically one thing let me tell you, the difference between Ohm's law and electromagnetic induction. Okay, in Ohm's law V equal to Ri or IR, whatever it may be. So if you have current, voltage will be there. If you have current of 0, voltage will be 0. But in electromagnetic induction, how much current is flowing in AD? 0. There is no current flowing in AD, but still voltage is induced or not? Yes, because that particular turn is influenced by change of magnetic field. So this AD, let me write it as a isolated winding. Now just we may have to try what is conducted power, what is inducted power, what is total power. Okay, now in two winding transformer, what was the conclusion we got? Okay, in two winding transformer, in dealing with MMS. Okay, for example, in two winding transformer, all of you has to focus here please. Okay, now in two winding transformer, secondary MMF was equal to primary MMF or not? No load current, forget about no load current. Okay, so secondary MMF was equal to primary MMF. Now for example, if I say 10 kVA machine transformer, that 10 kVA, is it related to primary or secondary? Both. Okay, so secondary MMF equal to primary MMF once you neglect no load current. Okay, so primary MMF equal to secondary MMF. Okay, primary power handling capacity is nothing but secondary power handling capacity is nothing but total power handled by transformer action without having any electrical connection. Okay, because in two winding transformer, how much was the resistance between primary and secondary? 0. Okay, so without having any electrical contact between primary and secondary, means power can be transformed, that is transformer action. Now for example, if you think of generator to utilization, generation to utilization, how power is being transmitted? By having directly transmission line, distribution line. Okay, so by directly having electrical connection, we can transform power or transmit power, means transmission line. So by directly having electrical connection, we can transmit power. Without having any electrical connection like transformer, we can transform power. Now if you see, transformer action is taking place. Okay, the moment transformer action is taking place means that without having any electrical connection, power is going to be transformed. Now is it having direct electrical connection or not? Yes. So because of this direct electrical connection, power will be conducted or transmitted or not, like transmission line. Yes. So how much power is being transformed by transformer action? How much power is being transmitted by electrical connection or conducted power? We have to calculate. Now let us go back to two-winding transformer. In two-winding transformer, primary MMF was equal to secondary MMF. Primary MMF, primary power handling capacity, secondary MMF, secondary power handling capacity. So primary power handling capacity is nothing but secondary power handling capacity is nothing but total power transformed by transformer action in two-winding transformer without having any electrical connection. Okay. Now keep that point in mind. Now let us think of lossless condition of auto transformer. Okay. So in this case, if I2 is the secondary current, let me think of this as I1. Okay, forget about no load current. Forget about no load current. If you forget about no load current, like means if whenever I2 is exists, then only I1 is going to exist. Okay, no load currents are neglected. Now, if I1 is injecting here in this area, how much is the current? I1. And I2 is going from here. So in this area, how much is the current? I2 minus I1. So I1 is entering from here, I2 minus I1 is entering from here, such that I2 is going to leave from here if you apply KCL here. Okay. Now let us think of in lossless conditions. What is input power equal to output power? So V1 I1 cos theta 1 equal to V2 I2 cos theta 2. Okay. For time being, let us assume theta 1 equal to theta 2. Okay, under that condition, what is V1 here? V1 is nothing but E1. So E1 I1 equal to E2 I2. What is E1? EMF per turn into number of turns. So EMF per turn into number of turns in primary N2 I1 equal to EMF per turn into N2 I2. EMF per turn, EMF per turn. Okay, N1 I1 equal to N2 I2. So okay, now is it MMF equation or not? Is it MMF equation or not? No. No. It means we should not think of like number of turns into current, ampere turns, MMF. No. In order to say that it is an MMF, I1 should flow through N1 MMF, I2 should flow through N2 MMF. For example, in two-winding transformer, I1 was flowing through N1 MMF, I2 was flowing through N2 MMF. But now if you think of auto transformer, okay, so in auto transformer, what is happening here? This is going to be N1, right? From here to here is going to be N1. From here to here is going to be N2. For example, okay, let me write here. This is going to be N2 number of turns, and this is going to be N1 number of turns. Okay, so if I see here total N1 number of turns and here N2 number of turns, secondary turns. So in complete N1 turns, is I1 is flowing? No, means N1 minus N2 in this part only I1 is going. Okay, now through N2 turns is I2 is flowing? No, through N2 turns I2 minus I1 is flowing. Okay, so I2 minus I1 into N2 can be MMF, or I1 into N1 minus N2, this part is going to be MMF, but I cannot say N1 I1 as MMF or N2 I2 as MMF, right? It is not MMF equation, but it's a power equation, not MMF. Not MMF equation. Okay, now means I said that transformer action is going to take place, no? Okay, so our conclusion here is transformer action is taking place. So the moment transformer action is taking place in two-winding transformer, primary MMF was equal to secondary MMF. So in transformer action in two-winding transformer, primary MMF was equal to secondary MMF. Primary power handling capacity is nothing but secondary power handling capacity is nothing but from primary to secondary power handled by transformer action without having conduction, without having any electrical connection. Okay, so see here in this also we should have some part of the MMF should be equal to another part of the MMF. Then I can say, for example, X winding MMF equal to Y winding MMF. Okay, then what does it mean? X winding MMF is nothing but X power handling capacity. Y winding MMF is nothing but Y power handling capacity. This power handling capacity equal to this power handling capacity means that either this or this power handling capacity is going to be power handled from input to output by transformer action without having any electrical connection. So let me calculate MMF of AB. MMF of AB is how much? N1 minus N2 into I1, okay, is going to be N1 I1 minus N2 I2. From our previous equation, N1 I1 equal to N2 I2, so this is going to be N2 I2 minus N1 I1 equal to N2 I2, N2 this is I1, okay, N2 I1, so this is going to be N2 into I2 minus I1. Now what is this N2 into I2 minus I1? N2 into I2 minus I1 is nothing but in our previous diagram, N2 minus I1, N2 into I2 minus I1 is nothing but N2 number of turns here, okay, N2 number of turns here, and current flowing is I2 minus I1, okay. So N2 into I2 minus I1 is going to be MMF of combined winding. So if I come back to here, this is going to be MMF of BC. Frankly speaking, auto transformer is over. We'll be able to solve all the problems. Okay. So MMF of AB is nothing but separate winding. MMF of BC is nothing but combined winding. So MMF of combined equal to MMF of separate. So by two winding transformer, what is the conclusion here? Power handling capacity of this or power handling capacities of this is nothing but power to be handled by the auto transformer by transformer action without having any electrical connection. So S transformed by transformer action is nothing but S of combined or S of separate. Now what is meant by power transformed or transmitted because of electrical connection? Okay, now S total is going to be how much? Total power input is how much? V1 I1 or V2 I2. Okay, so this is going to be V1 I1 is the input or V2 I2 is the output. Okay, now V1 I1 or V2 I2 is the total. Already transformer, you know what is conducted power? Conducted power equal to S total minus S of transformer action. So with this, frankly speaking, more than sufficient to solve all gate problems. Only one small thing is there. We are going to deal that separately. Let us solve problems soon.